Okay, moving along, let's talk about Raman spectroscopy. And I expect you probably haven't spent a lot of time talking about this in your other classes, because this is generally like a pretty heavy P-Chem technique, even though it is really useful to any and all branches of chemistry. So let's talk about the Raman effect. So a molecule must be anisotropically polarizable in our selection rules. And so that's to have a Raman spectrum. And so what that means to be anisotropically polarizable, as the molecule enters some electric field, shown by E here, if its molecular orbitals can be distorted in this anisotropic way, then it will give rise to a Raman spectrum. So what these ovals are showing you are the MOs, the molecular orbitals. And you might be asking, what is this electric field? Well, it's light. So recall, light is an oscillating electromagnet, right? Given by all of these various dipole moments. So if we bathe a molecule in a high intensity electric field or a high intensity amount of light, we can distort its molecular orbitals. And when that incident radiation scatters off of the molecule in this like kind of grazing angle type of way, we see different wavelengths being affected differently. So for example, our Rayleigh scattered light, we could kind of think of this as analogous to our specular reflection. So there is no change in wavelength in the Rayleigh scattered light. In the anti-Stokes scattered light, there is a change in wavelength. And in the Stokes scattered light, there is also a change in wavelength. And what's important to note here, that this is a very rare effect. Typically like 1 and 10 to the 7th photons will actually exhibit anti-Stokes or Stokes scattering. So you have to use a very intense source of radiation for this effect to occur. And typically that is done with a green laser operating at 532 nanometers. So it's a monochromatic source of incident radiation, but we get a wide distribution of frequencies coming off of this molecule. And the way that these are scattered, the anti-Stokes and Stokes, are based off of the vibrational levels. So here's a better picture to describe that. So, and just kind of going back to the basics, right? Here is our vibrational energy levels. There are the new levels. So infrared absorption, right, just puts us up one level at a time. And we can see now here this whole notion of this thing called the virtual energy states. So these virtual energy states are this scattered electronic environment. So virtual energy states, or I should say the distorted electronic environment. So Rayleigh scattering, there's no change in wavelength. In the Stokes scattering, Stokes-Raman scattering, so you can see here, this is our scattered Stokes line that comes back to us, and it comes back to us with less energy. So the Stokes scattered light is red shifted. And then now what you can see here, the anti-Stokes Raman scattered light corresponds to a higher wavelength, so it is blue shifted. And it's important to note here that these are only shifted by the vibrational energy levels. So because we're using this like visible wavelength to do this, it's tempting at first to think that we're going to be like massively shifting things into the blue end of the spectrum or the red end of the spectrum, but not really. The amount of shift that happens is actually quite small because it corresponds to single vibrational levels. So the way that this technique is done is the following, and there's several different ways to do this, but this is a general scheme where we have our laser, and typically, as I said, that's a 532 nanometer green laser. So that goes through a beam splitter where some of the light will focus down on the sample and some of the light will scatter back up to the detector. So the light that goes back down to the sample is also refocused back through these optics. So that's what the beam splitter will do. This filter will block out the green laser. So block out this because this laser, the green laser intensity will outweigh all of the Stokes and anti-Stokes shifts by a lot. So it will completely blow out our detector. So we filter out the green laser light. And then what we get are the Stokes and anti-Stokes scattered light. And those are visible light, right? Those are visible wavelengths that are detected usually on a CCD. But again, the differences between these correspond to the vibrational energy levels. So here is a look at what Raman spectra might look like. So for example, the 532 would be the Rayleigh line corresponding to 0 Raman shift, and that will be hugely intense. That's why it's kind of showing this big, fat, huge peak. So that's why we want to filter it out. So again, the Stokes shift we typically view that as shifting positive, and the anti-Stokes shift we view as shifting negative. They give the same values, right? The Stokes lines are typically higher in intensity because the Stokes lines emanate from the nu equals 0 state, which has a higher population at room temperature, right? The anti-Stokes lines will be typically lower in intensity because there is much lower population at the excited vibrational states. And this Raman shift can be calculated as the following: 1 over the lambda 0 value minus 1 over the lambda 1. And so lambda 1, for example, if we find this peak here, wherever it might be in the visible spectrum, right, we would plug that visible line in, compute this, and that would give us the delta omega, or in other words, the vibrational energy level. And so you can see this is showing you that this shifts on the order of wave numbers, even though we're using visible light to detect it. So the advantage of using Raman versus IR is that our normal modes that don't involve a dipole moment change are visible in a Raman spectra, which is kind of cool. So for example, here is CO2. And if you recall, our normal mode, so this is our FTIR up here, and this is our Raman up here. So that peak that was occurring at 1388, the V symmetric, that is IR inactive, but Raman active. And similarly, the VA symmetric stretch, that is IR active, is not Raman active. And the bending stretch that is IR active is not Raman active. So this means, like, if you can do both, if you can get an FTIR spectra and a Raman spectra, you get an ultimate characterization of a molecule. So this is IR versus Raman spectra of benzene. So that's what we're looking at right here. And you can see there are some peaks that line up. So some peaks that are both Raman active and IR active, and some peaks that are not. So other molecules that display Raman spectra that do not display FTIR spectra are things like O2 and N2. Those are not IR active, but they are Raman active. So again, being able to use like both techniques, if you can, gives a better characterization than just one. Okay, folks, so we'll talk a lot more about Raman in our live lecture. I'll see you then.